Welcome, everyone. For today's prep, we're going to look at reading graphs of derivatives. And we're going to see particularly, or what we're going to be looking at in this section, is what kind of information can we extract about some original function, f, if we're given the graph of its first derivative, or what kind of information can we get about the original function f if we're only given the graph of its second derivative. And I think this is the one we're going to start with because, it's actually a little bit easier. So we're going to kind of do what we've been doing. We're going to, given the second derivative, we're going to see how we can figure out the intervals of concavity for the original function, and then also how to figure out where the inflection points happen. But it's going to be a slightly different feel to it because we're not going to be calculating the second derivative. What we're going to do is we're going to be given the graph of the second derivative. And we're going to use that graph to uncover information about the original function. All right, so let's pause on the first derivative stuff here. Maybe we'll come back to it, or we'll come back to it in class. We'll see. But let's start with the second derivative. All right, so what do we know about the second derivative? Well, we've used this computationally to find the intervals of where the original function is concave up or concave down. So we've seen before, if we're looking at an interval from a to b, if our second derivative is greater than 0, so if our second derivative is positive, then the original function f is concave up on that interval. And if our second derivative is negative, if it's less than 0, then the original function f is concave down on that interval. What we're going to be doing here, though, is in example 1, we're going to be given the graph of f double prime. So the graph that we have here, this is not our original function. This is the graph of f double prime. And what we're going to try to do is we're going to try to uncover as much information about the original function as we can. So this curve here, this is f double prime. All right, so normally, if we want to find the intervals of concavity for a function, we calculate the second derivative, and then we look for the possible inflection numbers. Well, we don't have a formula here to kind of differentiate, but we do have the graph. And we're going to start off. We're going to look for the possible inflection numbers. And the possible inflection numbers, well, there's two things we're looking for. This is where the second derivative is either 0 or where the second derivative is undefined. And again, why are we interested in these two places? Well, if we go back, in order to figure out the intervals of concavity, we want to know when is the second derivative either positive or negative. And so the only way you can switch from being positive to negative, or the other way around, is one of two options. You either go across the x-axis, so that's what this is, literally go across the x-axis like this, or if it doesn't exist, maybe you jump across the x-axis. All right, so let's start with f double prime equal to 0. So these are essentially the x-intercepts. Where does it cross the x-axis for the graph of f double prime? So we want to know where does this cross the x-axis? And on this one we see, well, there's two places. So we've got it crosses there at x equals 0, and then it crosses again at x equals 3. So we've got two x-intercepts. Okay. Now, does the second derivative not exist anywhere? Well, if we look, all of the points are on the graph. So if the second derivative didn't exist, you might see something like an open dot, open hole in the graph, or maybe like a jump or something. But we don't see any of that here. All the points on this graph are filled in. So in this case, no place where the second derivative doesn't exist. Okay. So what we have here is two possible spots where we might have an inflection point. So if we remember back, when we were doing this computationally, once we have these x values, then we do our sign chart. And the graph is enough information to do our sign chart. So that's what we're going to do next. We're going to do the sign chart for f double prime. So we draw our x-axis. And let me slide this up here. Okay. And then we plot our, in this case, 2 possible inflection points. So we've got 0 and 3. And those split up our x-axis into 3 separate sections. So we've got the interval minus infinity to 0, 0 to 3, and then 3 to infinity. And what we want to do is we want to figure out, is f double prime positive or negative on each of those intervals? And once we know that, we'll be able to say if f is either concave up or concave down. All right, so let's start with the first interval, minus infinity to 0. So that interval, if we look at our graph, corresponds to this section of the x-axis. Okay, so pick a test number somewhere in this interval and look at the corresponding point on the graph. So maybe -1. Look at the corresponding point on the graph. And all we're interested in is knowing, is the value of the function either positive or negative? So the fact that our curve here is above the x-axis, well, the y value is going to be positive, +2 if our test number is -1. So what we're seeing is that on this section, the graph of f double prime is positive. And if f double prime is positive on that interval, it means the original function is concave up. So just to kind of go back up, if we're given the graph of f double prime, what we're really looking for is f double prime is positive, means that f double prime is above the x-axis. And if f double prime is negative, what we're really looking for is just where is it below the x-axis? When does our graph dip below? So that's kind of graphically what we're looking for here. We're still trying to figure out when is it positive or negative, but you can just kind of look at where is it above or below. So if we go to our next interval, well, here we're in between 0 and 3. So now we're in between here. And if you want to think of it with like test numbers, again, pick a test number. So maybe like x equals 1. And then you're just looking for where is the point on the graph. And it looks like we're right here. And the y value for that point is -1. So we're negative. But really, what we're seeing is that this section of our curve, f double prime, is below the x-axis. So that means f double prime is negative there, which means our original function f is concave down on that interval. And then finally, for our last interval, if we're looking from 3 onward, that corresponds to this section of our x-axis. And again, we see that it's above the x-axis. The graph of f double prime is above, so it's going to be positive. Or if you wanted to think of it with test numbers, pick a test number, so maybe like 4. Look at the corresponding point on the graph, and you see that there's this point here, and the y value there is +2. So again, a couple different ways to think of it. So it's positive, which means on this interval, our graph of the original function f is concave up. So what we found, if we interpret our sign chart here, is that on this first interval, the original function is going to be concave up. On the second interval, it's going to be concave down. And then lastly, it's back to concave up. So we can write all that out. So f is concave up on the interval, what do we say, minus infinity to 0, and on the interval 3 to infinity. And then f is concave down on the stuff in between, that interval 0 to 3. Okay. So then we need to know, for the second part here, what are the x values where f has an inflection point? So again, we want to go back to our list of possible inflection numbers. Now these are the places where we might have an inflection point, but we're not guaranteed that we actually do have an inflection point at these places. So that's why we say possible. But if the original function f is going to have an inflection point, these are the only places where it could happen. So the little bit extra that we have to do is we have to go back to our sign chart and see if we change concavity at each of those places. So we look at x equals 0, and what do we see? Well, we go from concave up on one side to concave down on the other side. So there is a change. So that means we are going to have an inflection point at x equals 0. And then we do the same thing for x equals 3, and we see also there's a change there. We go from concave down on one side, and then on the other side, we're concave up. So there is a change there as well. So it's possible with graphs, you might be concave up on one side, and then, still concave up on the other side. So you don't necessarily have to have a change in concavity, but in this case we do. So our x values here are x equals 0 and x equals 3. And just a quick note, we don't have enough information for the y coordinates. Well, not enough info for the y coordinates. And the reason is because the graph that we're looking at, this is the graph of f double prime, not the graph of the original function f. So yeah, the y coordinate for these points is both 0, but that doesn't mean the original function has to have a y coordinate of 0 for those points. So we don't actually have enough info to get the y coordinate for what the original function is doing at each of these places. All we know is that these are the locations where f is going to have an inflection point. Okay. So, again, the tricky thing with these types of problems is we're looking at the graph of f double prime. So when you look at this graph, if we're talking about the intervals of concavity, you might think, well, yeah, this graph is always concave up. But we're not investigating whether this graph is concave up. We're trying to figure out whether the graph of the original function is concave up or concave down. So we don't have the graph of that original function. What we're doing is we're interpreting the graph of this second derivative to see what information we do have about this second derivative. What does it tell us about the original function? So the answers that we're getting here are not about the graph that we're looking at. They're about some unknown graph that we don't have. We're trying to kind of extract as much information as we can. Okay. So I think that's a good break-in point. In class, maybe we'll try another one of these second derivative ones, but we're going to go back and kind of review over what the first derivative tells us about the original function, and we'll try some examples. So we'll see you then. Bye-bye.